The method that we have used to construct a linear approximation to a function leads us also to give a little bit of a more formal foundation for a concept that we have used sort of underhandedly before, and that we're going to use again later because it turns out to be a very useful tool in calculus, and that's of course the tool called differentials. So I'm going to give you a little bit of an explanation for what these differentials are, and I'm going to tell you in a minute why you might find that confusing, and that's okay. But the confusion will go away as you work with these things. So let's start first of all from remembering once again that the derivative of a function can be written as dy by dx with the Leibniz notation or with f prime of x. And that because f prime of x is a limit, this is going to be approximately equal to f of x plus h minus f of x over h as long as h is small enough. But if h is actually a non-zero but small number, the top of that fraction is really just the difference in the y-coordinates of the points on the function corresponding to x and x plus h, and the bottom is just the difference between x and x plus h. So the top is the difference between the y-coordinates, the bottom is the difference between the x-coordinates. So I can write that with the usual change notation, difference notation, with delta y over delta x. Alright. So what I can do now is I can look at this sequence of equalities and almost equalities and approximate equalities, and I can try to set up some kind of relationship between dy and delta y and dx and delta x. And again, it's going to be an approximation, but as I said, it turns out to be an approximation that works. So what we're going to try to do is interpret dx and dy as small changes in x and y. But we have to do that carefully. So how are we going to do that? Well, it turns out that the following method works well. So what we're going to do is we're going to say, all right, there is really no difference between delta x, change in y, and change in x, and simply dx. Okay? And they're both the same thing that we called h in the past. We're assuming that this is a small number, and we're going to make them equal to each other. So dx by itself just means delta x, and we're going to call that the differential of x. For y, the situation is different. For y, what we're going to do is we're going to look at that equality in the first equality and do something that we've done before in situations like the chain rule and things like this. We're going to pretend that the left hand side is a real fraction. We're going to multiply both sides by dx, and we're going to define dy as being just f prime of x times dx, and we're going to call that the differential of y. Because of that sequence of equalities and approximations up on the top, we can say that dy is going to be approximately equal to delta y. Not the same, but approximately equal. And therefore, it's going to give us a good approximation of the change in y. And now again, remember, as I said, you may probably feel at this point that you're a little bit confused, that we really, are you tricking us with these things? Well, if you're feeling uncomfortable at that, you're in good company. There are, in fact, certain theoretical mathematicians who really feel uncomfortable about this whole idea, that they don't feel that it's really well defined, and they've started they've started some time ago a new branch of mathematics called non-standard analysis. We're not going to go there, but you may want to look on your own what that is. But basically, the idea is try to define these differentials in a more formal and a more solid and a more convincing way for them. But as I said, as long as you think of these ones as approximations and you work with them, they work well. Okay? So the point is that they're useful in many situations, so we will be using them in the future, both in terms of using them for approximating the change in y and the change in x, as well as for all kinds of other things that we're going to do later.